The problem is this won't be part of the previous recording. I can try to make it where I think we just may have lost the other one because when it kicked out, it hasn't had a chance to convert. Now, if I can get the other one back up, that computer might actually be dead. If I can get the other one back up, that'll be great. If not, by the way, this is one of those areas I do have extensive videos already posted. I don't know has anybody actually looked at them yet?
Not the Green's theorem.
I have extensive videos on Green's theorem and on examples. I did more examples on the videos than I did in class today. So you can actually get everything from the class. You can actually look at the YouTube. They're the YouTube videos, but I've already put them on Canvas. So we do have an out if this doesn't work. I'm a little disappointed that I have a computer that just died. You know, it gave me 1 minute of warning. Anyway.
Why is that nx? Why is it 3y squared?
The partial of n with respect, did I write down correctly?
Unless
partial of this with respect to x is going to be 3y squared times the derivative of e to the x, which is just 3y squared e to the x. Did I? Oh,
okay.
Sorry, that's what you're saying. Okay. Now, what do you notice about nx minus my? Do you notice anything?
It equals 0.
Oh, so that means the answer to my question is what?
0.
So the original line integral, you know, in 6 months when you get tired of trying to, you know, hammer through it, the answer is 0. How could the answer be 0? Anybody want to guess? How come the answer is 0?
Is it a conservative?
Because it's conservative. In 2 dimensions, what's the only test for conservative? Do you remember we did that last week? The only test for conservative in 2 dimensions is nx equal to my. That was the test for conservative. Oh yeah, the cross partials thing. I gave you a conservative force, which automatically means the integral is path independent. So how does that help me? Path independent, remember, only matters where you begin and where you end. So you evaluate the end minus the beginning. But if ending and beginning are the same place, we're not saying we're taking 0 minus 0. No, we're taking not 0 minus 0. We're taking something minus something, but something minus the same thing. I'm not subtracting 0 from 0. I'm taking big quantity minus big quantity and getting 0. So one of the best parts about Green's theorem is if you have a conservative vector, Green's theorem will produce an answer of 0 as it's supposed to. So in this problem here, if I didn't have Green's theorem, there's no way. There's no way we could parameterize and then evaluate that new integral. That would be beyond, you know, beyond comprehension, unfathomable, as we say, you know, beyond fathom. But Green's theorem says essentially, if you have a closed loop, look at the double integral. Okay, as long as you can state it. Now, you may end up having to use polar coordinates. That's not a big deal. But this integration here, I'm maintaining is pretty much always going to be easier than this integration here. Now, one of the best parts about Green's theorem, let me give you a simple example. This one was excellent. I mean, we all agree this was great. All right, I want to do an integral. Let's say the integrals of the following form. It's e to the inverse tan of x minus y cubed dx plus, how about 4x minus 6 natural log of the inverse sine of e to the x. How's that? That looks pretty nasty. Okay, I want to do this. Yikes. Now, I don't even care what the path is. I have a closed path. That one's worse than the previous one, by the way. E to the inverse sine of x. I mean, come on, who does that? I'm sorry, that's a y, not an x. Sorry, what am I thinking? Now, I want to use Green's theorem. Why? Because it's a closed loop. What is my? Anybody? What's my?
Negative 3y squared.
Yeah, you're thinking about it. You don't need to think about this. What's nx?
I was making sure I wasn't integrating.
Okay, not yet. What's nx?
4.
4. So that means this is equal to the double integral over whatever the region is of this minus this. I think that's pretty not scary. That's horrifying. That's even more horrifying. But you notice what I did? I put the horrifying function of x in the dx, and I put the horrifying function of y with the dy. They both go away when I do the partial derivatives. So a huge advantage to Green's theorem is a lot of times the nastiest terms not around at the end. So now that you've seen how to use Green's theorem, you've seen where it's derived, you don't actually have to think about it. If you have a closed loop, you're automatically 100% of the time going to use Green's theorem. There would be no advantage to doing multiple line integrals with the parameterizations because you have to do multiple different parameterizations. Okay, so that's where we are. That's what I wanted to get done.